Good afternoon. I'm Professor Sever. Today we're going to do an introduction to abstract vector spaces and subspaces. We have already studied subspaces of the Euclidean space Rn, namely the column space and the null space of a matrix. So now we're looking at vector spaces in an abstract setting. So first, let's look at the definition. Vector space over the real numbers. In other courses, in higher level courses, you would look at other fields. This is where the scalars come from rather than just the reals. You could look at the complexes, for example. But right now we're looking at vector spaces over the reals. The definition is as follows. A vector space is a non-empty set V of objects, called vectors, on which we define two abstract operations, addition and multiplication. And the multiplication is scalar multiplication. The addition is the addition of objects in V, which is vector addition. Subject to some axioms, and this is an axiomatic approach to the definition. So first, we're looking at arbitrary vectors u, v, and w in V, and scalars c and d. First, closure. Number one is closure. The sum of any two objects in V is also in V. We say this is closure. In other words, you can't get outside of the space by vector addition. So if u and v are inside of the vector space V, then their sum has to be inside the space. If V is a vector space, mind you, and of course that's what we're imagining. We're imagining it will in fact satisfy all 10 of these properties. A simple example is, let's consider the odd integers. So let V be the set of odd integers. If u and v are odd, u plus v is not odd, it's even. So in this case, addition on the set of odd integers is not closed because the sum of two objects in the set would not also be in the set. Number two, commutative. U plus v is v plus u. And just a side note, I'm writing circle plus here to try to illustrate it's an abstract operation. Since we don't know what v is, we don't really know what the operation is, except that it's called plus, and it satisfies these axioms. The next one is associativity. Typical the way you would write associativity, u plus v plus w is the same as if you shifted the placement of the parentheses. Namely, if you added v and w first, then added it to u, you again would get the same result. If you did u plus v first, then added that to w. On the left, of course. Again, it doesn't matter in a sense since it's commutative, but again, that's the way this is written. Number four is identity or additive identity. There is a vector, a zero vector in the space. We're going to write it as bold zero. Sometimes we write it as a z. Here we write it as a bold zero, and it's the additive identity for the space, V. U plus zero is u for all u in V. And this has the precise property that you would expect an additive identity to have. When you add it to a vector, it doesn't change the vector. Number five, there's an inverse. Already we're front-loading the notation, it's minus u, but technically you really wouldn't do this first. You would say it's a vector y in V such that u plus y is 0, but we know that the inverse is unique. We know by a theorem. So what we're saying is we're just naming it here. We're going to call it minus u. Now at this time, this is not minus 1 times u, because we haven't discussed the scalar multiplication yet, although it in fact will be equal to that. But right now this is just notation. What is it notation for? The additive inverse of u. That's namely that special vector such that when you add it to u, you get the 0 vector. 6. Now we're doing scalar multiplication. I'm writing it as circle star, again to show the potential abstractness of the operation. If you take a vector u in the space V, multiply it by any constant, that result is also back in V. Again, closure with respect to scalar multiplication. And again, the integers, I used the odd integers last time. The even integers wouldn't be closed because even though integer plus integer is integer, our scalars come from the field of real numbers. So if we did 5/2 times 3, 5/2 is a scalar, or even the square root of 2 would be a good example. Square root of 2 times 3, or 5/2 times 3, neither one of those is an integer. So that's just an example. You have to remember that the scalars come from the real numbers, field of real numbers. So 7, which is distribution, Scalar multiplication distributes over vector addition. So that's what this means. This is a scalar addition distributes over scalar multiplication. It's another type of distributive. This is a kind of a pseudo-associative type operation. And of course, number 10 says there is a multiplicative identity. 1 times anything is itself. So 1 times u is u for all vectors u. And this says there, and this is not an arbitrary number 1 or an abstract. This is the number 1 in the real numbers. This is the number 1 that you're familiar with. This is not the 0 vector in Euclidean space or 0 number in the reals that you're familiar with. This is whatever the 0 vector would be in the particular space at hand, which would be V in this case. I'm Professor Sever, and that concludes part 1 of an introduction into vector spaces. In part 2 of this series, we will look at abstract proofs and delve a little more deeply into this subject matter. Thank you.